Alright, hell yeah, we have dynamics, and this is part 9 of a series of doing differentiation. And this is kind of a difficult problem. We've done differentiation a bunch of ways. In this video, we're going to do it as a function of time, because the coolness is we're going to plug it into a derivative calculator, and when you do this, you have to derive just with one variable. And so if you want the change in position, with the derivative of the change in time, then your variable has to be time. You can't have theta in here, you know what I mean? Changing, because what we're going to do is we're going to get the length of this. We've done that in all the videos. And then we're going to take the derivative of it. But if we take the length of this in terms of this angle theta, cool. We can know what the change in length is when we change this angle. So taking the derivative with respect to theta means, hey, I'm going to move this angle like 30 degrees. What was the change in this height? That's all. You know, it doesn't give you the speed. So, but if we find an equation for theta as a function of time, then hell yeah. Then we can say, hey, in 0.01 seconds, this goes 60 degrees. And now what's my change in this follower? You know what I mean? And so then I'll have this change in distance, and then we'll have the change in time of 0.01, and that'll give us the velocity. And by taking the derivative of this, we'll get a derivative, which will be the velocity as a function of time. And then what we're going to do is basically say, cool, once we get that derivative, well, wasn't theta just omega t? So anywhere where we see omega t, we can just throw in theta. And so this is kind of cool because now we do have an equation as a function of time. This would be velocity of that follower A as a function of time. But we could also easily get it as a function of theta, because we'll just replace these with theta. But what you can't do is throw in this equation in the derivative calculator if you have theta in here, because that'll just take the derivative of this equation with respect to theta, and that's not velocity. You have to use the chain rule to get velocity. And so and then so even with the second derivative, these things are monstrous just because you have so many, you know, like you have to take this times the derivative of that plus that times the derivative of this. So every time that you have a product of two things that need a derivative or a quotient, you know what I mean? Hell yeah, that's going to be, you're going to get three things there. And what I would do, instead of using the quotient rule, just bring this upstairs and call it this to the negative half. But still, you're going to, when you take the derivative of these three things, you're going to get like 1, 2, 3 different things. And then finally the derivative of this is just a constant, so you'll get that fourth thing. So at least you can see why this problem, if you took the third derivative, holy hell, you would have one thing here, one thing here. So that would be two things. This would be two things. This would be another three things. And this would be a fourth thing. So we have 1, 2, 3, 4, 5, 6, 7, 8. You would have 8 separate ridiculousnesses. But still, if you want to get this is your acceleration of that follower as a function of time, but if you want it as a function of angle, hell yeah, you just throw in the angle there. Okay, so we have a couple different problems. This problem says your speed, your omega, is constant. And this problem says, hey, let's do it if we have some angular acceleration. We're going to start with 0 speed, and then we're going to progressively get faster and faster. So that derivative is going to be like here. So here's the differences between the two equations. So in all the other, and I guess let's slow down. So let's see what the geometry says, see how we get this equation. And then for one, we're going to say theta is just omega t because we don't have any acceleration. But for this one, we're going to have some acceleration. But we only have this term because we don't have an initial angular speed. And we're going to see how that's very similar to... so getting this, getting theta as a function of t is very similar to, you know, kind of the classic, hey, I'm going to go cliff jumping into some water. My velocity here is 0, but we know we have acceleration, let's say, of 10. And so we need to take that and say that this acceleration is dv dt. It's the change in velocity, change in time. And then we can integrate. So we separate variables. This becomes 10t plus a constant. And basically it's velocity. At time 0, my velocity is 0. Okay, so my constant is 0. So, and then you do the same thing. This is change in position, change in time. Separate variables, integrate again. You get position is going to be half this acceleration. So we're going to have 5t squared. And if we had an initial velocity, then we would have that c, whatever our constant is here, would be our velocity initial. We just have a velocity initial of 0. And then, so basically, yeah, your kinematic equation can be 1/2 acceleration t squared plus velocity initial times t plus initial position. But in this case, hell yeah, our initial position is 0, and we're going to say this is maybe the positive distance direction. Okay, so those simple things that may be more intuitive when you're looking at something in linear motion, jumping off a cliff, but it's analogous to something spinning. So for this problem, we have an angular speed of 104.7 radians. I'm just going to call it omega. But it's also, you know, change in, the definition of angular speed is change in angle, you know, in a unit time. This thing is changing in angle. It's going to go 6,000 revolutions per minute. That's 17 times a second. And so here's the factor label. 1,000 divided by 60 is that kind of 17 times 2 pi radians, and we get 104.7 radians per second. But this thing's going 6,000 degrees per second. So it's going, you know what I mean? It's going 60 degrees in 100th of a second. So we'll hit this 60 degrees in a time of 0.01 seconds. And so keep that in mind. Okay, so angular speed is change in angle, change in time. d theta dt. And so we have that. So just as we said acceleration is 10, and then we said that that's equal to this derivative of change in velocity, change in time, definition of acceleration, then we can integrate. Now if we didn't have any acceleration, but we did have some initial velocity, then we would start the integration process there. That's the same thing here. We don't have, for this problem, angular acceleration is 0, but we do have a constant speed of this thing spinning. Okay, so we separate variables and we integrate. So we get an equation for theta is that angular speed, 104.7 radians, times time. And so, and does that make sense? If I have something that's 104.7 radians per second, what happens if I multiply by 1 second? You know what I mean? If my speed is 104.7 radians per second, in 1 second I'm going to go 104.7 radians. Well, hell yeah, there's 6 radians in a circle. And so 10 divided by 6, don't know what that is, but 10 divided by 10 is 10. 10 divided by 6 is that 17 I was talking about. This thing's spinning 17 times in 1 second. Okay, hell yeah. So, but what we did here is we took angular speed times time, and this gave us the radians that got played out. You know what I mean? So that's going to give us the angle. So the angle is omega t. So, sorry I'm just kind of rushing through this, but no, I think we're doing a pretty good job. And the same thing, if we had an initial angle, like for this problem, we're going to start at the angle of 0. So at time is equal to 0, theta is equal to 0, so our constant is 0. And how you do that is you say like, hey, I'm going to throw a 0 in here for my angle, 104.7 times 0, plus a constant. Well, the constant has to be 0. So right here, this is an equation. You know what I mean? Even though that it has the constant, we just need one location where we know theta and time, and right at the beginning, that's usually always going to be the case. Okay, sweet. And so there's my equation for theta as a function of time. You could reverse it and find, divide this by 104.7, and you have time as a function of theta. Okay, hell yeah. So now, when we do this problem and it says acceleration is a constant, we're going to do that same thing. We're going to say, hey, this acceleration is dw dt, and we're going to separate variables, integrate, and we're going to get angular speed is this angular acceleration times time plus a constant. We know this problem says at angle of 0, time 0, angle 0, the speed is 0. The angular speed is 0. So hell yeah. Angular speed is 0 at time 0. So that means that if we put 0 here and 0 here, this constant has to be 0. Hell yeah. So now we have an equation for angular speed. We have to say angular speed is change in angle, change in time. And we get an equation, and then we separate variables and integrate again. And we're going to have, since we have a time here, this goes t to the 1 plus 1 divided by 1 plus 1. And so we have 1/2 angular acceleration t squared. That's our equation for theta. You can bring this t upstairs, divide by alpha, take the square root of it. You can get the equation as a function of t. Okay, sweet. And let me go over this real fast, I guess. So this problem, when you play out some sort of angle, we do have an eccentricity here. It just means it's wonky and lopsided. So this distance is 60 millimeters, but it's a constant. This distance doesn't change. Radius is 100 millimeters. It also doesn't change. So we set up the geometry, and we really want to know this distance. If we know this distance is a function of theta, we're in business, because then we can take the derivative of y. So we can say dy dt, even though y is a function of theta, all this stuff theta, well, we can use the chain rule. We can say, well, I know what I can get the velocity dy dt by taking dy d theta, and then do that, and then multiply by d theta dt. You know what I mean? Because these two things can cancel, and they cancel kind of theoretically, because once you take the derivative, you're just like, you kind of lose that term. It becomes part of the derivative, but then you just take it, and then d theta dt is that omega. And for this problem, that's a constant. All right, hell yeah. But the general gist is you get this length y, from the pivot point O to A in terms of theta. And so we do that by saying, hey, I know this is the hypotenuse, I know this is theta. If I have a triangle, especially a right triangle, all I need to know is two things, and then I know everything about the triangle. So this opposite is the sine component, e sine theta. This adjacent is the e cosine theta. So booyah. This triangle, though, I only know, I only know this radius. I really don't know this angle. But I do know this side is e sine theta. Okay, and that's a function of theta. So I do know two things. We use the Pythagorean theorem kind of in reverse. I don't know what both sides are, but I do know the hypotenuse. So I take the hypotenuse squared minus this squared and take the square root of that. So that's this equation. This, I would definitely memorize that. You know what I mean? We all know that this side squared plus this side squared equals that. But let's say you don't know this side. Then it's the larger number squared minus. It's got to be minus, right? You know what I mean? A larger number minus this squared. And then hell yeah, square root it, and you got this side. So sweet. So that's where we get this equation as a function of theta. It's this plus this. But now for both these problems, we need to insert our equation for theta. So in this problem, where we just have a constant angular speed, theta just becomes omega t. So we just throw that in. Hell yeah. And then we throw it into the derivative calculator, and we're just money, because it does it. It loves it. You know what I mean? And it pops out this, and then it pops out this. 100% accurate. And the cool thing about the derivative calculator, especially for this problem, because we have numbers to input, is, let me pull up the graph. Where the hell is the graph? Sorry about this. All right, so yeah, we can, because we can throw in. Now, E, when you throw it into the derivative calculator, is a number, so I have to use that as C. You know what I mean? So in my equation, I have everywhere where you see C, that is C is E, but all the other variables are the same. So we have angular speed is W or omega, and time is going to be 0.01 because time of 0.01, like I said, that's an angle of 60 degrees. And what it wants to know is the velocity of this follower when the angle is 60. So booyah. And so this was 104.7 radians per second. That's our angular speed. 100 millimeters is our radius. Eccentricity is 60 millimeters away from that radius. Time is 0.01 seconds. And booyah, it's going to give us the height, you know what I mean? Let's work backwards. We were trying to find this distance y. Well, yeah, it says it's 115 millimeters. But cool, when we take the derivative, it also tells us how much that's changing. It's changing by, it's going down, this follower is going down the negative direction at a speed of 7,000 millimeters per second, or 7.3 meters per second. So hell yeah, it's traveling pretty fast, because this thing's spinning hella. And then the second derivative will tell you how much that's changing. It's actually getting faster. You know what I mean? We have a negative, the negative direction means the follower is going this way. And then because the acceleration is also in the negative direction, it's actually speeding up. You know what I mean? So hell yeah. And, alright, hell yeah. And this might be the last time I get to break out this, this thing that I made. But, you know, I set up the problem where this is the actual disk. This just shows the disk in one location, but this is how it spins. And so we can see from angle 0, the slider would be up at that green arrow. I did this at 45 degree angles, so 45 is that one, another 45 hits there, and then another 45 hits there. So you can see from here to there it's going real slow and going real slow on the way up. It picks up speed and then goes hella fast. So this blue one is 60 degrees right here. And you can see, well, I don't know. I mean, I guess we know that it's hella fast right there. And from our equation, we know that it's actually getting faster as it travels from there to, you know, right about here. And then it starts to slow down again. Okay, hell yeah. All right, sweet. So what we're going to go over is, so here's the inputs. And obviously this was theta, you know, for one problem. The problem with acceleration, this was theta. And booyah. So this is the problem with just the constant speed. And so yeah, anywhere where we see omega t, we can input theta. Now the one with, now this problem was brutal. Like, it's not in the back of the book, but it literally says find the acceleration of the follower as a function of theta. That's the second derivative. And that's the one with, and that's the one where you have your angle is the angular acceleration, 1/2 angular acceleration time squared. You know what I mean? So this is the velocity as a function at any given time. So this one just says, and then when you get the equation, hell yeah, you can find. What you're going to find is the velocity of this follower at any time, given that it's starting at 0 speed, 0 angle, and then, you know, having a constant acceleration. Basically, that's nuts. I mean, you could consider it like, hey, if there's a motor here and you turn on the motor for that first second, hell yeah, you might have constant acceleration until you get kind of into the upper limits of speed, but, you know, and then then you'll actually lose acceleration because you'll have constant speed. But yeah, just know that any problem with constant acceleration for sure must have a limit. You know, the problem is only applicable for that constant speed. If something's constantly speeding up, it'll literally reach the speed of light pretty fast. Alright, so yeah, so nothing can constantly speed up forever. Alright, booyah. So, yep. And so let me go, so here's the inputs. Here is the one where theta is, so this is, to spell it out. This is our distance y. And that's the part that's like, that's kind of cool to me. It's just like, all differentiation for these problems kind of just start out with, hey, what's the length? And if you want to find velocity, that's the change in length per time. So we find a length, and then we differentiate, and that gives us the change in length per time. That's velocity. Hell yeah. So here's our inputs, and again, these are just that length y that we were talking about. And then so this is the one with the acceleration. So the first derivative of that looks like this. This gives us the velocity. But for that problem, they were like, hell yeah, what's the acceleration? And so, man, this is brutal, because this is the acceleration. Acceleration of that follower A, 1, 2, 3, 4, 5, 6 terms. But this is pretty cool, because everywhere where we see 1/2, so if we see, theta is 1/2 angular acceleration times squared. So anywhere where we see that, we can throw in theta. So everything in these parentheses is a theta. But this one, hell no. You have a time outside of the theta. So that's why we solve for t. We say that time is 2 theta divided by alpha square root, or 2 theta divided by alpha to the 1/2 power. And so what we're doing is we're saying, hey, every time where I see time, I'm actually going to input this equation for theta. Now, right here I said I had time, but I saw that there was a time squared, linked with angular acceleration and a 1/2. So I know that's literally the definition of theta. So I might need to slow down for this, but okay, right here I don't have a half, and I don't have just one angular acceleration, I have 2. But if I did, if I do have at least one angular acceleration, I have t squared, but I don't have a half. I have 2 of those. So I guess this would be 2 theta, but I still have another angular acceleration. So there you go. So anywhere where I see alpha squared, oh, and this has a c. So that has that c is the eccentricity e. So sorry about it. I did not see that. So we would have 2 theta alpha for the angular acceleration times e. Okay, hell yeah. But I think that does it. So let's take that one, alpha squared e, and then t squared. So let's just take the t squared. If we take this squared, we're going to get 2 theta alpha, and then we're going to multiply it by e alpha squared. So this one cancels one of those, and we got 2, exactly what we have. 2, I'll do this, 2e alpha theta. I don't know what order to put them in, but that's exactly what we get. So hell yeah, so everywhere where we see those, we can input that. But I think you get it, you know what I mean? Some of these aren't the same. That one, like this is a little bit different. Yep. But I think you get it. So, I mean, if you just wanted to say, hey, everywhere where I see a t squared, I'm going to input 2 theta divided by alpha. Cool. So I could just do that. I could say, hey, I see a lot of t squareds out here, so I'm just going to input this, and then you can just use this equation. And this equation would give you the angular acceleration of this follower as a function of theta then. So hell yeah, it's just a bunch of things theta. Everything else is a constant. Theta is the only thing changing after we do that. This equation, the only thing that's changing is time. Everything else is a constant. Alright, hell yeah. So I think we did it, and booyah. So, I guess I learned a lot. This is kind of the first major problem that I've done a few of these now on differentiation. I think the coolest part is like, hey, can you set them up? The setup is crucial, because it's using trigonometry. It's finding a length that you might change. You know what I mean? If you're trying to find the velocity of something, well, what's the distance to that? And can you link it to, you know, if we're having something spinning, can I link this distance to this angle change? And if I can, I'm in business, because then I can take the derivative of, well, I can take the derivative of this length and with respect to time, even though this is a function of theta. Well, I just use the chain rule. I take this with respect to theta and then multiply by that, you know, d theta dt, which is angular velocity. But hell yeah, if I'm going to use the derivative calculator, this video is just, we'll go one step further, figure out what the equation for theta is as a function of time, and then you're just money. You have an equation as a function of time, you can put it into the derivative calculator, and then booyah. You can pop it out. And the cool thing about the derivative calculator is, again, you know what I mean, you can input the values and get, you know, and get whatever, you know, for this one, it's going to be a function of time. So that's where if you're just like, hey, at 60 degrees, well, so that's kind of cool, because what we do is we go back, I guess we've been looking at this one. We go back to the equation and we say, hey, at 60 degrees, what time is that? Well, I'm going to put in 60 degrees right here. Obviously, change it to radians. And so that's going to be 1.047 radians. I guess I learned that from this video, that 1 radian is 1.047. Divide it by 104.7, and hell yeah, we got 100th of a second, or 0.01 seconds. So that's what we input right there. So sure, there's no input for theta, but that's what we did. We have an equation for time as a function of theta. Cool. Alright, so I'm done with this one. This was part 9. Thanks for joining me on this little series of differentiation. And hell yeah.